Hello and welcome to the Xapiens Podcast. I'm your host, Loyd Waites. I'm a particle physics student at MIT, also working in machine learning and nuclear medicine. Along the way, I've learned some really interesting things, but nothing compares quite to my favorite quote. It goes like this. The views of space and time which I wish to lay before you have sprung forth from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows. Only a kind of union between the two will preserve an independent reality. A man named Hermann Minkowski said this in 1908, describing some of the foundational ideas that would later go on to be Einstein's theory of general relativity. Over 100 years and $1 billion later, in 2017, the Nobel Prize was awarded to Rai Weiss for the discovery of gravitational waves. For the first time, deviations in space and time were observed using massive lasers over a mile long, forming an interferometer. Ray has to be one of the most interesting and hilarious people that I've met. His family literally fled the Nazis, moving to outside of Harlem. He then went to MIT, flunked out of MIT, came back, became a professor, and then won the Nobel Prize for one of the most important discoveries of our time. At 89 years old, I really don't think he slowed down at all. He was sending me emails in the middle of the night on weekends just to schedule this interview and was super energetic the entire time. So I hope you enjoy this interview. I know I did. Thanks for coming to talk with us today.
Well, thank you for having me.
Yeah, I mean, it's already been great talking to you so far. For people who aren't familiar with your work, do you mind if you just kind of give an overview of what you're working on now?
Yeah. What I'm doing now?
Yeah.
Oh, right now.
Right now.
Oh, I'm 89. That's the number one, okay? That holds you back in certain ways. You don't think as fast at 89 as you do at 50, I don't think. At least I find that. I get stuck factoring, okay, for example. So that's one of the tragedies. But I don't think you think a lot stupider. You have certain things better. General ideas are better. So it's worth getting old. Don't die young if you can avoid it. So what am I doing right now? Well, we have this thing which you got me to give you a talk about, which is this gravitational wave stuff. And I'll tell you exactly what we're doing. When we built LIGO, which is that instrument called the Laser Interferometer Gravitational Wave Observatory, nobody quite knew at what scale to make it. And the reason was we didn't really have the sensitivity. We sort of worked at making the sensitivity, and we didn't really have a good idea what the source strength was. And that wasn't just because we didn't know how to calculate what a black hole, if it did exist, how a black hole would radiate, because that was known well enough, even though the theory was very complicated. To factors of 2 or 3, you knew it, okay? That wasn't the problem. The real problem was how many of those suckers actually are out there. And there was a very strong movement within the MIT physics department. I'm thinking the epic I'm talking about is sort of the 1980s when this was all being formulated, who said there are no black holes. Black holes is a fiction of some crazy people. And Einstein didn't disagree with them. I mean, having an infinity in an equation didn't look good. But the infinity in the equation turned out to be a coordinate problem, not a fundamental problem. That sort of never really got appreciated. And anyway, so the real problem was we didn't know the number of sources we would detect. And we did what we could. We made the instrument 4 kilometers long. The LIGO instrument is an interferometer which has L shape like this. And it's a Michelson interferometer with some fancy stuff inside of it to make it more sensitive. We can talk about that more later. But you had to get to a sensitivity everybody realized that was at a level where you were measuring a strain, which is what a gravitational wave does. It makes a strain in space and time. But you can write it in such a way that it's only in space. I'll get to describing the wave later. But the thing is that the amount of strain theorists had calculated, and in particular, one of the more important theorists was Kip Thorne, who was at Caltech, and had dedicated a whole part of his theoretical group to trying to make sure that black hole physics was understood. He'd been trained earlier at Princeton, well, that was the sort of, not with Einstein, but with Wheeler, John Wheeler, who was sort of the person who coined the word black hole and took on all the strange stuff that came out of general relativity and tried to make sense of it geometrically. Wheeler and Kip got along very well, and Wheeler then influenced Kip. Kip went back to Caltech, started a group, and the first thing that he actually did, Kip, was to try to calculate what sources are out there and how big might the strain be that we could detect on the Earth from them. And the number that he came up with wasn't too bad, as you'll see. It was around 10 to the minus 21, a strain. Now, what is a strain? It's a change in length. Here are the 2 points, and let's say the distance between them is L, and then you say, let's say they move a little bit. That little tiny motion is delta L, and L is the big thing. So delta L divided by L is the strain. It's the same way a mechanical engineer would measure the stretch of a steel bar. You know, the steel bar is so long, you load it, and it gets shrunk a little bit because it's loaded. That's the way you measure strain in a real mechanical system. It turns out, and this is something we'll learn later if you care to, that space is a hell of a lot stiffer than steel. That's one of the things that most people don't understand. You can't do anything to space hardly at all. And that's why when you, even with a strain of 10 to the minus 21 coming at the Earth, the energy that's associated with that is unbelievable. The amount of energy associated with that wave, the amount of work that had to be done to strain space is gigantic. A number that's sort of interesting to use is, you take steel, the Young's modulus of steel, okay? And that's some number, okay? I don't remember. It's 10 to the 12 in units I love, which is units you guys don't use anymore. That's
CGS units?
The CGS units.
Yep,
I
my
can't
undergrad
get away
advisor
from CGS
loved
units.
CGS units.
I mean, you have to learn some other stuff, but
So they were God's units.
God, CGS is just wonderful. And anyway, so it's about 10 to the 12 dynes per centimeter squared. And if you take the stiffness of space and calculate that, you'll find out it's about 10 to the 20 times larger than that. 10 to the 20, 10 to the 20 larger than steel at about 100 hertz. It's frequency dependent. It depends on the frequency. The higher the frequency, the higher the force is needed to stress it. So and then the reason I make a big fuss about this is that, and I'll show you when we talk later on if we do want to talk about an observed source, I'll translate that into strain that you might feel in your body, and it's really just zilch. I mean, but anyway, the 10 to the minus 21 was the number that ultimately was used. It turned out to be about right. The very first thing we detected was around a strain of 10 to the minus 21. But what was that a product of? That was a product of, in the Einstein theory, what makes the strain? Well, the masses of the black holes. So these were 30 solar mass black holes. And they were spinning at each other at the end, they were going about 100 hertz, maybe 200 hertz, sort of C below middle C on the piano. Yeah. And those are very important numbers in the power calculation. And the other one is how far away it was. And that first black hole we saw was about 1 billion light years away. 1 billion, 10 to the 9. So anyway, and the strain we saw was 10 to the minus 21. Okay. So so going back to the early history of this, the problem was with trying to tell people that it was worth working on was that we didn't know the sources, we didn't know how many there would be, and most of them didn't believe you could measure something as small as that. So let me translate that 10 to the minus 21 into something else. We later on built LIGO is has 4 kilometer arms. And those 4 kilometer arms are the L in the denominator. So if you want to know what delta L you're talking about a few times 10 to the minus 18 meters. Okay? I hope I did that right. Yeah, a few times 10 to the minus 18 meters for 4 kilometers. Yeah, 10 to the 3, yeah. And so you're talking about something 1,000th the size of a nucleus, which you guys know better than I. So, and yet you're doing things with light. How the hell do you do that? That's going to be one of the questions. And so, but people even those days didn't believe you could do that. That was really the big problem. And that dean, who was a pain in the ass to me and later became provost, was a bigger pain in the ass, even when he became that. Didn't believe a word of it. And he had some faculty to support him. Okay. So that was the beginning of it. And now you ask me, what am I working on now? Well, I'm working on now that we've seen something, which is we've seen black holes, lots of them, up to about 90 pair binaries. We're trying to improve the apparatus right now. We're not running right now. They've seen two neutron stars, one neutron star beautifully, two neutron stars going around each other. That was probably one of the most interesting events that happened in astronomy in about 2017. We can talk about that if you get interested in it. And that gave us all sorts of results. And the reason why is it was seen not only by LIGO, it was seen also by Virgo, which is another gravitational wave detector. That one happens to be in Europe. And they have plans for the future too, which I'll get to in a second. Once it was identified with Virgo and LIGO together, we had many, many differences in time. Let me just say that this L that is the detector has no sensitivity in position. It's most sensitive for gravitational waves coming down on the plane of the L, coming down. But it's also sensitive at all angles. There's one angle where they don't respond at all, at 45 degrees, a cone of 45 degrees. And that was critical in the Virgo. Virgo didn't see it. They didn't see the neutron star binary. We did. And so they should have had the sensitivity to see it. And so we guessed it must have been in that zone of silence of that 45 degrees. And that was a good guess, because when we put that in to the solution of where is that source, and you do it only by timing, the same way you do nuclear physics experiments. Right. You can't point nuclear physics experiments. You measure time, distances, stuff like that. So yeah, this is not a telescope that you can aim. Okay. So what happens is that you need the more differences in time you have, the better you can determine where the source is on the sky. You need more detectors also, with something I haven't told you, that gravitational waves come in two polarizations. I'll get to that later. You have to separate the polarization. That means, how does a stretch take place? Maybe I should say it now. I mean, the two modes of the two polarizations, just like in electric field, you have linear polarization this way and that way, okay? And circular polarization that way and this way. In gravity waves, because it's a spin-2 field, it's quadrupole radiation in the end. What comes of it is that the polarization is, and this is now telling you what the gravitational wave looks like. Maybe I should show it to you. Yeah, now this thing, what you're seeing here, is you see all those dots? Those are just places that pick out points in space. Now, all these dots, these will get to move in a minute, but this dot right there, which has a red square around it, I can't see it as well as your camera can. That's you. That's you standing there. And the gravitational wave is coming out of that board or going into it, okay? Now let's get it started, and you'll see what the gravitational wave does by looking at what the dots do. So let me hit this. All right. If you look at that for a while, you'll know, first of all, you'll get dizzy, but the other thing is that you'll notice that there's motion in one direction. The wave is coming at you. The velocity propagation speed is out of the board. Call that the z direction. And so when there is expansion in the x direction, which is perpendicular to the z, there is contraction in the y, and a little bit later, half a period later, it's the opposite. Y contracts and x expands. I hope you can see that. Right. That's absolutely critical to the detection process. But that's also the polarization of the wave. See, you can rotate that picture by 45 degrees, and you'll find out they're orthogonal to each other. Right. Okay, that's the interesting thing about geometry. And okay, so that's one thing to notice. The other thing you'll notice is the gravitational wave, and now you can see the actual field that makes the gravitational wave. If you look at, let's say, the two dots here where you are standing, and look at the most distant ones away, they're moving a lot. And the two near you are hardly moving at all. Can you see that?
Right.
Yeah.
It's going to be length dependent.
That's right. So it turns out that the field quantity is delta L over L. That's the strain. And when you do that, it's the same as stretching a rubber membrane. Okay, if you make marks on a rubber membrane and you stretch it, you will see that that looks just like that.
Same kind of idea of when you have like universal expansion and the things that are going farther away are much more redshifted.
Be careful with that one.
Okay.
Be careful. I don't think I can quite agree with that.
Okay.
Okay. There is a little bit of the geometry like that in there, but this quadrupolar geometry isn't part of the universe. Anyway, I think that's the image you want of what a gravitational wave is. At any rate, the thing we didn't know how to do is gauge, well, money ultimately determines the length of the apparatus. Let's face it. And in this sort of field that we were in fact, that guy whose picture is up there thought he had seen gravitational waves back in the 1960s. That's Joe Weber, and with an apparatus that he claimed would see gravitational waves. And a lot of people, what I love about physics is the experiment wasn't so hard that not 10 people in our country and another 10 people all over the world did the experiment that he did over again. And they saw nothing. I mean, within 2 years, it was determined that he wasn't seeing anything. And that led to some very unpleasant physics society meetings, by the way, in which what happened is Joe Weber, who is an interesting man, but he went a little bit daft, I think, about this. He would say, yeah, you haven't seen anything because you didn't do it my way. And that's not an argument in physics, thank God. Some of these guys said, we did it better than you did, and we don't see anything. And we can prove it, we did it better than you did. And that turned into these vast arguments. And the field got that's where the field got a very bad reputation. And that's part of why that dean, who I dislike, and provost, the same guy who I dislike, probably was not totally unjustified in being skeptical. But he was too skeptical, okay? But that was sort of the flavor of the field. It was a nutso field. Only crazy people got into it. And Weber was considered a nutso, okay? And he wasn't a nutso. He was actually quite brilliant, and he had a very clever idea that you should even try to look for this. And Einstein had said many, many years before that, in 1916, he already said that when he made some numbers for himself about gravitational waves, at the very end, by the way, this paper is on the web, translated into English, so anybody can go look at it. It's the 1916 paper on perturbation expansions of the general relativity, of the equations of general relativity, where he does certain calculations. He shows that you get the perihelion advance for Mercury. He shows that it makes Newton physics in the limit of weak fields. And for the first time in his life, Einstein talks about gravitational waves, pretty much with what I just showed you. But what he gets very wrong, by the way, is how the sources make the waves themselves. He gets that wrong, not in the quantitative way, but in a qualitative way. In fact, I'll tell you what happens in that paper. He thinks, because of the way he formulated the equations, that what makes gravitational waves is he clearly saw that gravitational waves were being made by objects very much like electromagnetic waves are made by acceleration of charge. He saw that they were made by acceleration of matter. So a thing that goes smash into each other, that makes gravitational waves. Two things going around each other in orbit, they make gravitational waves. And that was honest stuff, and he had it right. But he also made a prediction there because of a mistake he made, that things that are uniformly expanding and contracting, like a soap bubble, you blow it up, suck it up, blow it up, suck it in, blow it up, that would also radiate. And that's not true. That's monopole radiation. That would not be quadrupole radiation. So it turns out that he screwed up, but he did at the end of that paper, the numbers that he had, the powers of C that were involved, the powers of big G that were involved, the powers of frequency that were involved. All of that was about right. And he plugs us in just like you or I would. I've asked the Einstein people to go find the back of the envelope he used. They claim there isn't one. I'm sure there is one. Because he didn't put it in his paper. He didn't put the calculation in his paper, but he only puts the result in. He says that when you look at that equation, what is in at the end of the paper, and you put the numbers into it, you'll find out this will never play a role in physics at all. And you have to think what Einstein might have known, And I want to see I did the calculation for him, because I was curious what he might have done. He probably had what's the biggest thing he could imagine in 1916? 2 trains smashing into each other. Okay, well, 2 trains smashing into each other. You do that calculation using the elemental formulae that Einstein had, and they were right, the formulas were almost right, you would get in the radiation zone, which is about 300 kilometers away. In a collision like that, you have to get away from the induced field. You have to get out into the radiation zone. So at least one wavelength away. And for the times involved, it's about 300 kilometers away. At 300 kilometers, when these two trains smash into each other at 100 miles an hour each, it's a pretty good collision, killing a lot of people. The thing has only got a strain as measured at that distance of 10 to the minus 42. Okay? So that was clear that Einstein said this is never going to be measured by anybody. And so then he probably thought of something else. He probably thought of binary stars. They were known. I mean, they were not known the way we know them. We know of little compact binaries, which are very important. But there are binaries in our own galaxy, which are made of ordinary white dwarf stars. So those are electron degenerate stars. And they're electron degenerate object. It's pretty small. It's much smaller than the sun. Has the mass of the sun, but is much smaller.
Yeah, that's right.
And so two white dwarfs going around each other could have a period of 8 hours without tearing each other apart, or even, And how long would you have to wait if you looked at one with a telescope for the thing to see that's losing energy by them falling toward each other and the waves coming out? You're not going to see the waves, but you should see the loss of energy into the waves. And you make the number and you'll find out it takes something like the age of the universe to see a change. So, it was hopeless. And that's why Einstein wrote, it's never going to play a role. And so here this guy, who was a little bit nutty, decided to challenge that. And he made an experiment which was only a factor of 1 million off the mark. His sensitivity was 10 to the minus 16 strain. You had to be, we did it. And later on, Kip and others, as I told you, had 10 to the minus 21. And that, it's 10 to the minus 15, that's about 1 million in strain. So in energy, it's 10 to the 10 they were off, okay? 10 to the 12. It's 10 to the minus, 10 to the minus 6, 10 to the minus 12, So it looked pretty dismal. So anyway, let me get back to, you asked what I was doing. It's a big, long story. You get everything you want except the answer to the question you asked. We're thinking now knowing more about what's out there, with the right scale would have been 40 kilometers, not 4 kilometers. And that is, in fact, what we're pushing right now. And what I'm doing to help out is, since I helped build the vacuum system for the 4 kilometers, as I say, I'm a plumber. I'm trying to figure out how you can make that cheap enough to afford it. And, I've been trying to interest people in the Department of Energy in this little problem I'm about to tell you about. Maybe this will be good advertising. Let's see. What it is that all the big expense in a 40-kilometer system is in the tubing. You have to have ultra-high vacuum. Otherwise, you get scattering of the laser light. And that scattering causes phase shifts, and it will screw up the signal. That's a noise you just get rid of. You can't have it. So you have to operate at, for example, at 40 kilometers, you certainly don't want any heavy molecules. It's death on wheels if you have any hydrocarbons. That's for other reasons, but this particular molecule with a gigantic dipole moment and slowly ambling through your field, that's bad news. No, but what comes out of most vacuum systems, even very good ones, is a lot of hydrogen. Every accelerator you are going to be mixed up with has a background of hydrogen. Most people they can pump it away easily, and it doesn't do a lot. Hydrogen's quite small.
Sometimes it actually helps.
What?
Sometimes it actually helps.
Well, it might help for certain things, but hydrogen, that's one thing. But the one that's really a pain in the ass is the water. And the water, every time you open up, you have to pump out and heat it or most accelerators don't want to do that because they have to get their magnets off, and they don't want to depolarize their magnets. So they wait. And I remember talking to people at CERN lately, and they're dying for having a system which has very much less water and heat absorbed on it. So that's some of the things we're working on, trying to figure out how do you make, not stainless steel is very expensive. So if you use ordinary steel, that's the other idea. Ordinary carbon steel, the kind of stuff that cars are made of, okay? That might save a hell of a lot of money, and I'll give you what it might save. And I think the high energy people ought to be interested in this. So I've yet to go to high energy people and ask for money. I've been asking for money from the NSF so we can study this with some vacuum people. But I'll give you a number. If we build the 40-kilometer system, as we built LIGO, which attained all the vacuum we needed, and it has the vacuum in it, that's good enough for the 40-kilometer system too. That would, if you take that and extrapolate the cost of only the big tubes to a distance from 4 kilometers, well, it's actually 16 kilometers, because you have 4 kilometers, you have 8 kilometers at both sites. We have 2 sites. I know how much that cost and how much effort that was. So we had 16 kilometers of stainless steel tubing, 4 feet in diameter. That's what's, see, very different than the tubes you guys have. You have these little tubes, and you have to, well, they are that big? I didn't realize they were.
Yeah, we have big 6-way crosses.
Really?
Yeah,
It doesn't get this size?
I mean, we have some things like that for like attaching stuff on, but
Okay, well, that's then you can almost think that it can be pumped out by not as many pumps. But you look at the early accelerators; they were like that, because the volume of the magnet was the real problem. And anyway, so no, now that's good. You got a bigger vacuum. That gives you a better chance of. Now, okay, so let me finish that thought. So what happens is, if you take that 16 kilometers of stainless steel, and having prepared it so it has less hydrogen outgassing, that's a preparation you do to it, and you bake it out at 150 degrees C for a month, and pump on it like hell, that's sort of what was done. That cost us all of that, and building the tubes and the supports for it and everything outside of the real experiment. That would, in $28, which is sort of hoping we can get started in 2028, would cost us about $680 million, just the vacuum system alone, if we built it just like LIGO. Now, if we can somehow manage to get rid of stainless steel, manage to get rid of a 150-degree bake-out, manage to get rid of the hydrogen another way, if you want. It turns out, and this is something that's very well known, the hydrogen, it turns out ordinary steel, ordinary carbon steel, has very little hydrogen in it. Turns out stainless steel is crawling with hydrogen. It's sort of, people made big mistakes years ago when they dumped on ordinary steel as being terrible vacuum material. It rusts. That you have to worry about. Yeah, you have to worry about what you might coat it with.
if you get rid of the water.
Well, the water, we're right in the middle of that right now.
Yeah.
It doesn't look any worse than it looks on stainless. Doesn't look worse. Okay? That's not good enough. I'd like to do something to make it a lot less. And we're thinking about putting coatings on, like silicon coatings. That's one idea, or that will get rid of it. So if you manage to do all those steps I just outlined, you could bring the cost down to half, about. So it's still expensive. It's sort of 300, call it 400 million. But that makes the thing, it's a break point for the National Science Foundation, because the detector will be about what it costs to make the LIGO detector. So it's another 150 million on top of that. And then the buildings, but the thing is more expensive than LIGO. LIGO itself, when the initial cost of LIGO, the initial phase of it was around, in round numbers, 200 million. And then you have to run it. That costs 50 million a year. And if you take that and put it together with the improvements, which were another 100 million, 150 million, you wind up that we have now spent, in the years we've been running this thing, $1 billion. Okay? And for the NSF, that's a big chunk of money. Yes. The DOE doesn't like $1 billion, but they can deal with $1 billion. NASA doesn't know how to, do anything less than $1 billion. No, I'm exaggerating, but that's space. Okay. So anyway, it makes it more feasible that we could get that kind of money if we can make the vacuum system cheaper. So that's the advertising. And I think I'm asking for some money from the NSF to do this, because it's interest of the NSF. But I've got some people at Fermilab, some vacuum engineers at Fermilab, and certainly vacuum engineers at CERN, who are very interested in this topic.
So it's ironic that you bring all this up, because at our ion source just down the street, which is only like 6 feet of vacuum tubing, our two biggest problems are contaminants and baking and expense.
And expense. So you've got the same problem.
Yeah.
Yeah.
And that's just a
well, would you build? Could you build
stand.
your thing out of ordinary steel, if it could be made so that it made no water and didn't outgas? It didn't outgas water. It doesn't outgas.
Didn't
hydrogen.
outgas. Yeah, I would think we could make it out of regular steel. There's no reason not to. Yeah.
That would save you a factor of 3 right there.
Right.
Huh. When are you going to build? When are you going to be building your thing?
So the test stand that we have is already built. We do have a test stand, but we are looking to upgrade it. So
Okay. Well,
That's-
anyway,
yeah.
so you should have a little bit of interest in this. It isn't earth-shattering. The rest of your experiment is comparable in cost to the vacuum system, I bet, or maybe more. You see, in our case, the vacuum system dominates. It dominates the whole cost of the whole thing because of that 40
it's so
kilometers.
huge. What kind of vacuum are you looking at?
Oh,
10
well,
to the
okay,
9,
we
10 to
10 to
the
minus 9 torr at minimum. We got, I mean, at the worst. We would prefer 10 to minus 10. And we get 10 to the minus 10 in the tube, in these 4-kilometer tubes that were baked at 150 C. And there were no leaks in them. Now, that was something else that I won't even go into that. That was workmanship. That was being real careful.
We're only at like 10 to the minus 6, 10 to the minus 7.
Yeah, well,
So
because you got
that's-
neutrinos. What? Oh, no, well, you got
Well,
electrons.
this is a proton beam.
The proton beam. So you do have to worry about scattering it.
Yeah, I mean, we take advantage of it because we get space charge compensation, where you get like the free electrons that will kind of decrease the amount of space charge.
Well,
at
you
high
hope to get some
intensity beams.
pumping out of the electrons. That's what you hope to do. Isn't that what you hope?
No, well, it's basically just trying to produce a proton beam, and then the proton beam causes a beta decay. So we don't want electrons except for space charge compensation.
Yeah, okay. Space charge compensation of the
Right.
main beam. Okay.
Right.
I see. Yeah, yeah.
Because it's a high intensity.
Well, you have lenses also, right? I mean,
Yeah.
along the way.
Yeah. So
I
we
see.
electrostatic and magnetic.
Well, of
lenses.
course. Yeah, I need both. Yeah. Well, anyway, so I think I've told you what I want to next in a very roundabout way, but you're going to do editing anyway.
Yeah. It'll all
So
get
I don't
counted.
feel bad about that.
Oh no, this is great. This has been
It
fantastic.
Just work for you. That's all. We have ambitious plans. Let's put it that way. Do you know Matt Evans, for example?
Yes, I do.
Good.
Yeah.
Well, Matt Evans is now the guy. Well, the girl and guy who runs the group is Nergis Mavalvala. She's the dean now, and Nergis was the mentor for Matt. I was the mentor for Nergis. It's a chain that goes on and on. And so Matt's now running the group. There is another professor who is interested in data analysis. That's Salvatore Vitale. Do you know? He's a very noisy guy, interesting noisy guy. And then that's the two faculty. And then there's some staff that is really absolutely essential to the place. A guy named Peter Fritschel, who is a senior research scientist in something called the Space Center, the Kavli Space Center. See, I mean, LNS started that whole idea of having a ladder of scientists who were not faculty but research faculty, effectively, like many universities have. But they started with I don't know if you know that, there's 3 positions they have. It's research scientist, it's just scientist, then research scientist, and senior research scientist. And these are the equivalent of assistant, associate, and full professor. And they have certain classes of tenure. They're not as privileged as the faculty, but look, they can't fire you. If they do decide that they can't get any money, they got to give you 3 years warning. Okay?
Wow.
Okay.
3 years.
Yeah, well, they used to. I don't know what it is now, but it was. It was designed so that you could find ways of employing people, well, in LNS in particular, people who didn't want to be faculty, wanted to do only research. And there was no easy way to do that. So LNS, which was nicely supported by DOE, and I think it still is. LNS is your lab, and that's still, I think, very much supported by the Department of Energy, right?
Yeah.
Yeah, this whole place had a single grant from the DOE,
I
and
get that,
it supported all the nuclear physics, all the high energy physics. And now you guys have branched into cosmology and all sorts. So you're getting a little diffuse for these guys, but let's see what happens. Yeah.
I know a bunch of people that are still on DOE experiments.
Yeah, well, a lot. Yeah. Anyway, the DOE was a wonderful lab, and when they threw me out of RLE, I wanted to go into LNS. But the dean wouldn't have it, the dean of science, who was a bit of a shithead. And I'll say that very publicly. His name was John Deutsch. And he's a guy who had quite different ideas than I did. And he had, first of all, no interest in gravitational waves because it looked cuckoo to him, as it did to a lot of other faculty. And the other problem was that he had no regard for people who never published much. And when you're building an experiment, you can't publish a lot. That's a problem. And if you're part of a big lab like DOE, there's data that you can analyze and publish something, but still work on an experiment that you couldn't publish yet. I don't know. I mean, I don't know, that's a complicated story, but I don't know how you do it now. But if you're working on, let's say, building a better accelerator for that, you're building, yeah, I think, Lloyd, you're building, that's right. You're building the accelerator in the Korea. And you're trying to do an underground, and you have to do some special things, and you have to learn how to do them. Some of that merits a paper in a nuclear equipment or nuclear instrumentation journal, but it isn't considered a scientific publication. And so, it's a quote, So you have to have some data that you analyze even to get a PhD or stuff like that. And so there is always a log of data that was taken, nobody analyzed in LNS. And a lot of people got through it that way. They built spark chambers and bubble chambers, and that was what they really did. But then to get a degree, they analyzed some data they probably had very little to do with, but they analyzed the living daylights out of it and got some result. And that was enough to get a PhD. So that was the way a lot of degrees were had. Yeah. Anyway, enough.
So here's kind of a fun question. So general relativity is something that captures a lot of people's imaginations, right? Because there's just so much going on, and it's such a weird concept to know that space and time are literally curved, and that's what leads to mass. Why do you think general relativity, even though it doesn't impact people's lives as much as something like medicine or biotech, why do you think general relativity captures so many people's imaginations? And why did it capture yours?
let's be really honest about it.
Okay.
I mean, in that talk, which I could show you the picture of, it's Einstein. Let's face it, a public hero. This is a very primitive. I'm looking at it in the most primitive way possible. And that's not the way physicists would look at it, but the society has made a hero out of Albert Einstein. And that was all due to Eddington in 1919, when he publicized that he had measured the bending of light around the sun with an experiment that I think barely showed it, okay? I mean, you can't do a chi-square fit to that experiment and walk away and saying they really measured it, okay? But they published it in the New York Times. And it was, the reason why it was such a big deal was because Eddington had used Einstein as a way of saying, we finally have found something which is wrong with Newton. And Newton was the thing that was dominating science and physics in general. And that was, if you read the paper, those papers of early life. So that's part of it. Einstein, if you ask I go to high school, grade schools a lot. I love to talk to kids. And I always ask them, well, name a scientist. It's always Einstein. There's never anybody else measured. It's just amazing. It doesn't matter whether you do it in Louisiana or you do it in the Pacific Northwest or here in Boston. It's Einstein. Now, nobody's as smart as Einstein. That kind of stuff. And it became part of the public culture. That's part of it. Now, why is it really interesting? That's much harder to answer. In truth, the Newtonian description of gravity was already absolutely incredible. And I'll tell you why. And that was why it was so hard to make this theory that was better. And that was, again, something that was philosophical rather than scientific. It was that Newton was the first, at least scientist that we know. Galileo may have been also, but I don't think so. And I don't know all the scientists in between Galileo and Newton who might have, but let's give it to Newton until you find out better, okay? And that is that he made an association between something that went on the ground, which was full of sin. The ground is full of sin. All of us sinners, okay? And there was this apple falling out of the tree. Forget about what fell out of the tree. Something fell down, and it predicted, the equation that predicted that explained the tides. It explained the solar system, okay? But now that's what's interesting about it. It explained the tides are still murky. They're on the ground. But the solar system, that's in heaven. That's in God's heaven. And that has no sin whatsoever. I'm exaggerating everything, of course.
No, I see what you're saying.
And the fact that Newton realized it and called it universal gravitation was the key idea. Here was something which operated off the earth, in the heavens, as well as on the earth. That was a brand new idea. really. And so it was a profound idea. Now, the fact that it worked so well, I mean, that F equals m1, m2 times g over r squared is a fantastic equation. It works still now. But it doesn't really work when you get to be fussy about it. And a couple of things you can be fussy about, which Newton, I would love to be able to have talked to Newton about this. I think other people would have also. Well, for example, one of the things that I don't know how Newton would have answered is suppose you take his theory, or the theory of just what we talked about, and say, okay, let's suppose somehow, very magically, God plucked the sun away, I mean, in an instant. Now, that would already magic. That's magic. But suppose, can you imagine what would happen if you plucked the sun away? What would happen? And if you take Newton's theory seriously, at least I think the way we teach it, you would say, all right, the Earth would begin to move in a tangent to the orbit right away, which is unbelievable crap. It can't be. Can't be right. Why? Because of Einstein. That's a piece of information that travels faster than the velocity of light. So there's something wrong right there already. And that's pretty subtle. And God, you only run into this when you get to something subtle. Like, for example, and you explain this to kids in high school or grade school, and they have their GPS out, they're going around, and they you know, and you tell them, look, if Einstein was wrong, or if Newton was the only thing, you wouldn't get home. You'd get to a place that's, you know, some number of blocks away. Why? Because the clocks on the Earth go at a different rate than the ones in orbit. And the ones on the Earth go more slowly than the ones in orbit. And so when you're counting clock ticks to determine the distance, you get the wrong answer. You know, you would wind up further away from home than you thought. And they sort of get the idea that that's the correction you have to make. So that's one problem. The other problem is you don't know what to do with masses that are moving at high speeds. And it turns out that those are the things that, for practical people, are the problems that with Newton. Now, why make it a geometric theory? And I can tell you where that came from. And to me, Einstein is one of these, he's a real hero. To me, he's a real hero. Why? Because he's not just a theorist. He thinks with his gut. He thinks down here. A little up here, a lot down there, I think. He wasn't the greatest mathematician that ever walked. He needed Marcel Grossman to explain the following thing to him. I think the way he got into this idea of geometry was from doing a calculation in special relativity, which is a stinker. How do you take care of the metric, or how do you make measurements on a rotating platform? Okay, a merry-go-round.
Right.
How do you do that? And what you have to do is somehow, you have to get your elements, the points that you, endpoints that the intervals you measure. Well, if you take radial distances and take the times radially, you'll find out that nothing much has changed due to the rotation. But if you measure circumferentially and pull the circumference all the way around, you'll find out the circumference is less than 2 pi r. And that says something funny. That says you've screwed around with the geometry somehow. And it gets worse and worse the faster that merry-go-round goes. It's not something you can deny. So, and it comes out that way. I mean, you can even use that to measure all sorts of nice relativistic effects. So I think that's first step, getting to understand the rotating platform, and then making what to him was the big step in that direction was to say, and dealing with the following issue, which was that something which we don't teach freshmen here well enough, although we try, that the different kinds of mass that we talk about, the mass you stick into inertia, that mass, why should that be the same as the source mass for gravity? It's a different object, a different idea entirely. Why should that be the same? And you can even break it down one step further. Why should it be the same mass as it receives the gravitational force? Okay? Well, there's a reciprocity between receiving the force and making the force. That's a reciprocity. That would screw up Newton's third law, so you best not mess with that. But why should the gravitational mass, the ability to deal with gravity, be the same as the inertial mass? And that was one of Einstein's, it was well known. Newton said it. He didn't think about it a lot. I'm sure he did, but he didn't know what to make of it. Bessel, the mathematician, later on also looked at this thing, and he thought about it a little more. And I don't think he made a theory for it, but he tried to figure out that there's something crazy here. He tried to measure a pendulum motion as a function of the mass that was on the end of the pendulum, and found that it was always g over m, the period of the pendulum, or the frequency of the square root of g over m, the omega of the pendulum. So he didn't see anything that would give them. So anyway, the idea, that's called the principle of equivalence, and that you extend deeper and deeper into the theory. What happens is that the geometry doesn't affect the other laws of physics. In other words, that if you make yourself freely falling anywhere in the universe, irrespective about the mass around you, suppose you're freely falling on very close to the event horizon of a black hole, you'll have a very small region around you where all the laws of physics, it won't be very big, but the laws of physics will be identical to though you had been very far from the black hole. That's the equivalence of the equations of physics are the same. Gravity does not affect the laws of gravity, whatever they are. So that idea that the principle of equivalence is sort of behind everything, and that you get the geometry is messed up by accelerations, and accelerations are like gravity. That whole business, that sort of triangle of thinking, was the basis of the general theory. And then Einstein had himself a terrible time doing the mathematics. And the guy named Marcel Grossmann, who was an old buddy of his, and his buddy also, the guy he always would exchange letters with, I don't remember, Bessel, they would discuss endlessly in letters to each other about what this geometry has to do with gravity. But in the end, it always came back to the rotating platform and the principle of equivalence. And so they kept on going. And then they found, Einstein and Bessel found, through Grossmann, that there was already a calculus that explained all of this. And it was a geometry of curved spaces, which Riemann had invented probably 50 years earlier, just as a mathematical exercise. So, I don't know, it's a long way around to answer your question. It's a much deeper theory. For us, it's a much deeper theory. It explains a lot more than Newton's theory does.
So is that what pulled you personally into doing?
Well, no. What pulled me? I can tell you what pulled me into it. I mean, that everybody has his own story. Mm-hmm. That had to do with that lab. Well, no, it wasn't there. It was over in Building 20 when the gentleman whose lab I told you where I got my degree, right across the hall from you guys. That was Gerald Zacharias. It was okay. I'll tell you the whole story. As a kid, for reasons that had to do with my love of music, I got very interested in reproduction of music. And you have to remember this was in the 40s, late 40s. I got interested in hi-fi, which later became a big business. And so I had all sorts of what I would call street knowledge. Street knowledge. I don't mean real knowledge. That's stuff what you pick up in scientific, like popular science, or you pick up from a radar manual that's put out by the military. You know, Ohm's law in all different forms, or that kind of shit. And anyway, I knew that sort of stuff, but anything deep I didn't know. But there was a very interesting thing that was happening in New York. I came out of New York, and we came to the United States in '39, but this was in the 40s. I don't know if that's something people don't remember, but New York. Neither are you from? I didn't ask you where you're from.
From Boston, actually.
You're actually in Boston, and he's from Essex. So, okay, so you guys are Boston. Okay, I think things happened here a lot later than they happened in New York. But in New York, what happened is that Edison got the east side of New York City electrified in the teens and the 20s of the last century. He had managed finally to lay cables, and the very first installation they made on the east side of New York. If you ever go to New York, you'll find out the fancy part. All the rich guys and girls live on Fifth Avenue, Madison Avenue, Lexington Avenue, and Park Avenue. That's where the rich people live. That's the east side of Manhattan. And the people who actually work with their hands and heads but have to work, they live on the west side. Okay. And they didn't have as much money as the people on the east side. So Edison decides he's going to electrify the east side first because he knows those people will pay for it. And what does he put in? He puts in DC, direct current, okay? And all right, they get DC and they get all these things that work on DC. And then on the west side, much later, about in the 30s, I wasn't there for that, and but that's when they electrified the east side. And by that time, it was Westinghouse and Tesla. It was no longer Eddington. And it was AC, 60 hertz AC, not 50 hertz like the Brits had. So now I come in the scene at the end of my electronics interest. I got really peaked at the end of the Second World War. And I was about, I was 13, 14. And it turned out people were buying electronics again after the war. All the electronics industry had been involved in making things for the war effort. But now, all of a sudden, people have been freed of that. 45 people, you could buy a radio again. And people made radios. Some people made radios that worked on DC, some made people on AC. Well, the average American didn't know the damn difference of AC and DC. And so what happened is the rich guys bought themselves the fanciest radios they could see. And they bought these things with more expensive. And they were AC radios. And they plug them in and they blow up. The transformer would blow up. Okay? And even though the plug wasn't quite right, but it wasn't like this. It was slightly curved, so you could smash it in. Okay? And that was just another piece of complete nonsense. And so I happened to be going to a private school. I had a scholarship to it because I was an immigrant. And the kids would come in with the busted radios, and they didn't know quite what to do with it. And I would look at them, and I said, I'll fix that for you. And at the time, there was all over New York, downtown New York, all this surplus stuff was coming back from the war. Transformers by the box load. You had varnish on them to avoid bacteria and what happens in high humidity places from gathering on and the capacitors and vacuum tubes, which you guys don't even know about.
I have one on my office.
You have a vacuum tube set in your office?
I have a vacuum tube
good
from
for
Fermi
you.
Lab
Okay,
in my office, yeah.
Good for you. Anyway, so, and you could buy it was just on the sidewalks. And you could buy transformers that would fix this. So I fixed the transformer, went and then fixed the plug so it was like this. And then they couldn't plug it in unless, whatever. And eventually, what happened is that they then had exchanges between the west side and the east side. And the kids on the east side, you could plug in a AC. You could plug a DC thing into AC. That didn't kill it. The other way around killed it.
Right.
So so I mean, it made a little smoke, but it wasn't as fierce a problem. Okay. So at any rate, eventually I started making a business out of fixing radios. I was in a tough neighborhood. I lived on the border between Harlem and Central Park, and I would bring these radios under my arm from school for the subway. And there was these Puerto Rican kids and some of the black kids. They would try to grab the radio from me, and so I would tell them, "Look, you leave me alone. I'll fix a radio for you." And boy, that was a real mistake because they would catch me. They would give me these radios that they'd stolen, and I'd have to fix them. So anyway, that was a whole thing. But the thing that got me started in electronics, and then the real thing that got me started in electronics was a movie theater in Brooklyn that had a fire behind the screen, and talking pictures were already going on. So there were some beautiful Altec Lansing speakers, 15-inch speakers with woofers and tweeters that were burned out. The cones were burned out, but the rest of it was okay. And that you could get for just unscrewing the speakers from the back of the screen. I knew about this because a guy told me about it. So a friend of mine and I got about 6, 7 real big loudspeakers. I mean, could put new cones in because he could get that. And then I made a FM set, and we could pick up the New York Philharmonic, which was live, not records, not tape recording, live. You could pick up the NBC, which had Toscanini, and you could pick these people up as live And by God, I had my room, I had a speaker and an FM set, and I would invite people in to listen to these concerts. They couldn't believe their ears. And so it didn't take long before everybody wanted exactly that. But make me one of those. And I made a few of them, and then I got into trouble. And I got into trouble with phonograph records. I know those are things you probably nowadays. Oh yeah, now it's become popular again.
They're coming back.
They're coming back in the vinyl form. They will never come back in the original form, which was the shellac form. Okay, the shellac. You know, the early. If you go in an old house or look at old records, the '78 records, they were all grooved. Just so they had a bigger needle, a 3 millimeter, a 3 mil needle rather than a 1 mil needle. I think. I know they went at 78 RPM, not 33 1/3. But they had a problem. Their problem was that they were made with shellac. I mean, they were made on wax, like the vinyls would have been, the originals. But then when they were impressed into something to sell it, that wax mold made a mark in shellac, and that shellac hardened. That had a surface which was not like sandpaper, but I would call it sandpaper, okay? And so what you heard was as the needle went along in the record groove, you heard, when the music was loud, it didn't bother you so much, but in a quiet movement, let's say a slow movement of a Beethoven sonata, something like that, where first of all, the playing was slow and quiet. All you heard was this horrible thing that's like that. You heard a little music, but that was absolutely awful. And that's when I realized that I said, well, you know, I could fix this if I could figure out how to make a circuit that had a bandwidth which changed width as a function of the amplitude of the signal. And the idea's okay, but then I implemented ideas that I could invent and make out of things that I knew without much mathematics. And they were worse than the cure. I mean, the cure was worse than the disease. Yeah. Okay? I mean, so I said, shit, I gotta learn more electronics. And so I applied to a couple of schools. MIT was one of them. And I got into MIT. God knows how that happened. It could have only been through my science teacher because I was not a good student. And so they got me into MIT, and as soon as I got here, I wanted to talk with people right away about how do you fix this crazy problem with records. But I came in as an electrical engineer, and they had none of it. They said, no, we have a very, very different curriculum in 1950 than it is now. The curriculum was rigid. You learned first about power systems. You learned how to make generators. You learned how to make motors. As a sophomore, you learned how to make transmission lines and all the problems of transmission lines. And that was the first course in electrical engineering. Electronics, what are you talking about? That's in a for seniors. And you couldn't really talk to faculty. They were not open. There was no Europe. There was nothing like that. So I got pissed off. And I mean, when I did the bridge truss for the 10th time, trying to figure out how to keep a bridge from falling down, which was one of the things you had to do, I said, the hell with it. And I looked at the courses that were available, and it turned out physics looked like it had the least requirements. That's a hell of a way to get into physics, but that's what it was. Okay, so that was the beginning. Then I got a job that summer. I won't go into everything. I'm coming to a point. You asked this question: how did I get into relativity? It requires all this bullshit first, and then I can answer it.
Well, you're just going through my list anyway. I was going to ask you about because I've heard that story of people stealing your radios in New York, and I thought that was the funniest thing. I was going to ask you to tell that story again.
Anyway, well, that's what happened, and you probably heard the whole story, but what the hell? And so what happened is that I worked for a guy who made a blood cell counter, automatic blood cell counter, who was a shyster. As far as I was concerned, he was trading on getting money from the military, entertaining the idea that you could have a nuclear war. The idea was if you could somehow make an attrition, a triage, enough, you could save a minimum number of people that would continue the people who would represent us as Homo sapiens. Okay. I mean, people were thinking that way. It was absolutely awful. And this was part of that. The military wanted to use weapons, nuclear weapons. They knew everybody had them. They thought they were trying to think, how could you use them and survive? And it was a completely mad thing, and people are trying to make money on this. This was awful. Anyway, That summer, I went and on a little trip to Nantucket. I ran into a lady who was spectacular, and I went completely gaga. I was young, total adolescent. Women were thinking that was something that you made up in your head, and so you fell in love in a way that normally one doesn't do anymore, or maybe people still do and they won't admit it. I don't know, but it was sort of so thorough that it took every moment of your day thinking about it. That's something that is quite destructive, but as an adolescent, that happens a lot. And so all I could think of was this incredible woman that I'd met. She was a pianist. She was a wonderful pianist. And so everything went fine until she decided she'd had enough of me. And then that was a bad time, and I flunked out of MIT. Now comes Zacharias. And I flunked out as a first-term junior, I think. Yeah, it was that summer between sophomore and junior. First term, that's when I flunked out. And I went looking for a job. And because I had all this electronics experience, I found a job in RLE. I knew about RLE because of of being drafted for the Korean War, and I was doing ROTC here in Building 20. Building 20 is gone. I don't know, you were probably too young to know about Building 20. Building 20 was the building before that, the big building with all the crazy
the
angles.
Status Center,
Yeah. It had plywood and asbestos shingles on the outside. Okay. We used to make hot tables with the asbestos so you could solder better. Anyway, and that lab is what did it. I won't go into how they hired me, but they needed an electronic person, and I was able to demonstrate enough knowledge for them that I was useful to them. And what they were working on was atomic clocks. And they started atomic clocks in that building, then it moved into here, right your way here. And what Gerald Zacharias had built was a small atomic clock, a big clock, about as tall as you are, and which now is sitting in the Smithsonian. It's in the Smithsonian in Washington, out of an atomic beam, using cesium atoms as the clock. And what they were doing is they were looking very carefully at the hyperfine structure transition in cesium, which was at about 9,000 megahertz. And that transition was used as a reference for the clock. And it made a clock that was better than anything anybody ever had before. Parton 10 to 11 in a year, and a little better than that in a month, and a little worse than that in an hour. In other words, the Earth is a terrible clock keeper. If you only use the Earth the way people had for centuries, and it wouldn't matter, you could only do things to Parton 10 to the 8. That's all the atmosphere and the water and everything on it, and all the atmosphere, everything slides around and causes the Earth to have an irregular period of that. So anyway, here was a clock that was Parton 10 to the 11, and the military used it right away. I mean, that's the basis of a lot of stuff we have, good and bad. And then I was a technician with him, and we got to be friends. For example, his mother was a piano virtuoso, Gerald's mother. He came from the South, and when I started learning the piano for myself at about 21, I would go to the launching school. I was learning one of the Beethoven piano violin sonatas, and I was whistling it. Whistling it, and all of a sudden I'm sitting on the floor above an experiment I'll tell you about in a minute, and all of a sudden the violin part comes from downstairs, and it's Gerald singing the violin part, whistling it, and I'm whistling the piano part. I couldn't believe it. So we became real buddies, okay? And and what was the experiment? The experiment was he was interested in making a clock that was good to a Parton 10 to the 13. And why was that? Because he introduced me to Einstein. He said, look, we ought to finally measure this difference in the way a clock runs in different gravitational potentials. And that was the aim of the experiment. And the way he introduced me to it was, you're young, you're going to be on the top of the Jungfrau. There's a lab up there, the Jungfrau in Switzerland. And he's older, he's going to be in the valley. And we both would have these 10 to the 13 clocks and send signals to each other. And we would notice that they would be off by a Parton 10 to 13 or Parton 10 to 12. And that sounded very exciting, and especially Einstein. My God, something to do with Einstein. That was really unbelievable. So I started reading all about Einstein. And that was the beginning. And then the clock didn't work. I won't go into all of it, but what the idea was very straightforward. The clock was supposed to be taking with the atom of the fast clock, the clock that only was part in 10 to 11, was a clock where the atoms went horizontally, like that, at thermal speed. The idea was to use the low end of the velocity distribution and just do that. Have it fall like a parabola. And of course, the books all said that's what would happen if you had a beam of atoms. It's not true. It turns out the books are wrong. There are no slow atoms. This is only for the slow end of the velocity distribution. It turns out, and I wish that hell the people would correct the equations for practical purposes. There are no slow atoms. And it took me about 4 or 5 years to really discover that. He had gone off and started revamping American education. But I couldn't stop it. I had to find out why the goddamn thing didn't work. And it turns out that what's very simple, what happens in a beam, the slow atoms are ambling along like this. They will eventually do that. But there are a hell of a lot more fast atoms, and they're peppering these guys, and then you throw them out of the beam. That's what happens. So there are no slow atoms in a beam of atoms. Just none. Now, nowadays, you can do this real easy. What you slow them down with a laser, and this thing that's called a Zacharias fountain, which is what this thing was supposed to be called, was indeed, so you can do that. Because now the average atom is doing that. And now you can make a clock that is really quite spectacular. You can lift it up by a centimeter right here in this office, and you can measure 10 to the minus 18 delta nu over nu difference of due to gravity just lifting up that. So that got me really going into worrying about Einstein.
That's amazing. So I've heard of studies doing like on a plateau versus sea level, but I didn't know that there were
talk to the guy, your neighbor. I don't know where. No, they're down. They're 2 floors down.
Yeah.
All the hot shots and the cold atoms are down.
Yeah, they're on the first and second floor.
The first level and second, aren't they also?
Yeah, first and second.
It's Kleppner's bunch. I mean, Kleppner's no longer there, but other guys. Yeah, other guys. Talk to them. It's not they who did it. The people who did it are the people at the Bureau of Standards or NIST in Boulder. They had to fix some things that bother LIGO, by the way. They had to fix the mirrors in a cavity. They had to make sure the mirrors didn't shake so much. The coating on the mirrors, which is not the mirror themselves, the coating on the mirror, shaking and having sound waves that are going up, causing thermal noise in the mirrors. And they had that trouble, and they had ions in the cavity. And these ion clocks are the ones that do the 10 to the minus 18. And they had to fix the mirrors first before they could get there. But now they have that, 10 to the minus 18. So it's really something. They can do things which are really wild. I mean, when you start talking about 10 to the minus 21 strain, you need another factor of 1,000, but I bet you they'll get there.
Yeah, I got to meet Eric Cornell a while ago. I think it was my first year in graduate school, who's over from Boulder doing in the atomic and optics group. Yeah. Really amazing guy. Did Bose-Einstein condensation.
Yeah, right.
And very, very insightful person. I was really
that?
glad to.
Was it
Eric Cornell?
Eric Cornell. Well, he was here.
Yeah. That's when I met him.
He was a student of Kleppner's.
And
Pritchard.
Oh, okay.
Pritchard. Yeah. The thing. It's very interesting. What happened here was sort of remarkable. The guy who first had the idea of trying to look for Einstein-Bose condensates, well, it were 2 people. It was Dan Kleppner, who was an atomic physicist, and oh boy, I hope I can remember I'll think of the guy's name. He's he's in solid state physics, who worked with Dan. I'll think of it as I talk. I can't get the name, but Dan is really the one who said, look, let's make a condensate. But he wanted to make a condensate of hydrogen. That's what he kept doing it with, and whose name I can't remember, damn it. They kept fighting all the different problems with hydrogen. Hydrogen turns out to be very, very hard to slow down. It has only high energy states. You can't get much energy out of the atom. You have to cool them by using laser light. But they were much more able to do that with all the alkalis, rubidium, cesium, and sodium. And the people who did that with laser light rather than trying to cool down by adiabatic demagnetization, for example, which is the way that Dan and this man who named them, I don't remember, they try to do it that way. And what happened is right in this building is where the first Bose condensate was made, on that floor.
Right.
And it was, you should get him on your little list.
Wolfgang Ketterle and Eric.
And Wolfgang had a couple of people who worked with him. It was Carl Wyman, and Cornell, And I think those were the two. The
Yeah.
three of them who won the Nobel Prize.
Yeah,
With that,
it
yeah.
was- yeah.
Yeah.
We're thinking about trying to get Wolfgang on as well.
No,
Yeah,
Wolfgang
yeah.
is interesting.
Yeah.
He'll tell you a lot about systems of units. I heard him
Yep.
talk about that.
Yeah.
I'm not so sure I agree with him. He knows I don't quite agree with him, but let him give you his story.
Yeah, I think he was measuring a kilogram by the number of photons.
Well, you got to
got
do something crazy like that to
Yeah.
go from one system of units to the other. Yeah.
Right.
Yeah.
So, I mean, science is moving very fast now. It continues to accelerate, especially in kind of the computation space with things like machine learning. Is that impacting LIGO and kind of gravitational astronomy, do you think?
Well, science is moving fast. Let me tell you. I think you can ask the question several ways. Would I, as a younger person, go into this field again? That's one way.
Okay.
Today, I think I would. And I'll give you the argument. But should anybody else? I think it's one of the areas of real unknown. In other words, I'm not saying that the area you're in is not an area of unknown. I mean, it'd be wonderful to understand the whole neutrino hierarchy, although it's closer to being understood than some of the stuff that we're trying to deal with. And is that really, is the standard model even right? But it seems to work pretty well, but it has some pieces that don't fit. So, I think gravity has the same problem, that don't fit. So, where are the challenges right now? I thought it's one of the big ones, and I know you guys are working on it, and I know that Peter worked on it, Peter Fisher worked on it, people all over, even people in gravity are now working on it. It's trying to identify what is the dark matter. And there's no question that dark matter exists. I don't think there's any question of that. You see it in galaxies, you can map it. I mean, it's not a fiction. And just the fact that it doesn't interact with light, that's too bad, but it interacts, other things interact with it, like other matter, because they interact gravitationally. So you can see the see with a quotation mark, you can see where the dark matter is, and it's not uniform. It's lumpy. So you see lumpiness. And the fact that you see it in galaxies, I mean, but when it wasn't called dark matter, yeah, it was called dark matter, but it didn't have the impact of being dark matter in the global sense until people began to realize that it affected also the cosmic background radiation. In other words, I think and that's when it became mysterious again. I mean, the dark matter could have been anything. It could have been anything, but it became very specialized as soon as we realized, and this is not often said what I'm about to say now, and you may disagree with me, okay? But once we realized that the structure in the cosmic background, the temperature fluctuations in the cosmic background add a part in 10 to the 5, 10 to the minus 5 Kelvin. The temperature is uniform with lumpiness at 10 to the minus 5. That's the RMS lumpiness. And how that spectrum, spatial spectrum, is made out, and that it has a Harrison-Zoldovich spectrum, all of that became known later, but what it's from. Where did it come from, this lumpiness? And you find out there's nothing that you can think of that would have made lumpiness on the scales that we see late in the universe. I mean, where the galaxies are, even, is responsive. The galaxy locations are responsive to that lumpiness. So it's really quite amazing. That lumpiness pervades. And where does it pervade from? It looks like it pervades from time t equals 0. Well, as close as you're willing to go with any theory about time at the time equals 0. I mean, in other words, it may have happened during inflation if inflation is the right theory. It might have happened near the end of inflation, but we now know that that's the only time when the universe was very small, spatially small, and communicative, that you could have made this kind of structure. And that structure was maintained and not disturbed by the heating of the universe that followed. In other words, somehow this lumpiness persisted through the goddamnedest chaos that existed as the universe got hotter and hotter and hotter and hotter and expanded. And how did it do that? It couldn't be ordinary matter because it would have been made uniform. So that's the real mystery of the dark matter. It really does not interact with infrared. It does not interact with light. And that was not completely known even when Vera Rubin first saw it with the galaxies. So it's a double mystery, but it became the same mystery. And so it's very important to find out what the hell the dark matter is, just for us, just for you, to get straight what it is. And I don't know if the axion is the right thing. It solves some problems I know about, but I can't vouch for that it's the answer. But that's nothing as bad as this goddamn dark energy.
Right.
That dark
Right.
energy is something
And,
like,
and so few people are looking into dark energy compared to dark
well,
matter.
you
It's
can't do
insane.
anything.
Yeah,
That's a real
because we don't know what it is.
Let me tell you a story about I.I. Rabi. I mean, I.I. Rabi was a famous atomic beamist. He was my mentor's mentor. He was a mentor for Zacharias. And Gerald told me a story about him when the muon was discovered. There's a famous story in physics, but you may not know it. And they had just discovered the muon they had discovered the muon in cosmic rays, because it's easy to see there. But Brookhaven had just made muons, and people had finally caught muons being made in an accelerator. And they told Rabi about this, and Rabi looked at them and said, "Who ordered that?" Because it just didn't fit into anything. Well, I look at that as the dark energy. Without that, we could have maybe lived a little longer. The dark energy is totally crazy. It doesn't fit anything, except something in general relativity again. And the other mistake Einstein thought he had made,
Cosmological constant.
the cosmological constant. Now, is that an accident that it fits? I mean, it's just another term in the Einstein field equations, which you can add. And Einstein recognized it in a completely cockamamie way. I mean, probably you know the story, otherwise you wouldn't have said it, but I will say it for your audience. And that is that Einstein knew only of a static universe. When he looked out there, it didn't look like anything was happening. Every night it looked the same to him. So he had to figure out a way to make gravity have a term that would have everything collapse on itself. I mean, a thing which has only gravity in it and nothing else would collapse. It just can't avoid it. So he thought about it, and he needed to make a thing that was anti-gravity, that pushed things apart a little bit. And then he invented the cosmological constant. And that, again, turns out to be unstable, but he didn't know it. That's why he called it his biggest mistake. Somebody pointed out later that even if you have these counter-operating 1 over r squareds, that's not stable. The second derivative of that system is not stable. So anyway, but it turns out that, yeah, this anti-gravity term seems to be needed in a couple of places. Inflation doesn't work without it. You got to have something like that. Right. And you have to explain the acceleration of the universe somehow. Now, I was very, very hard up about trying to accept the acceleration hypothesis. I mean, I'd been around long enough. I'd seen those people doing cosmology. And you tell me that with supernova, and I remember Perlmutter coming to MIT, and I gave him hell in a lecture, and the head of the department had to shut me up. I wouldn't want to, as Hermann Feschbach had to say, this is a guess, shut up. Okay? But what the problem was, so I wanted to know where were the mistakes. There were so many places for mistakes. I mean, this cosmic distance scale is just loaded with problems that make mistakes. And I thought it just was another mistake, because the Hubble constant had changed by factors of 10, then factors of 2, then factors of 1.5, and here now they're expecting me to believe 10%. Come on. Why all of a sudden should I believe it? And how do you take care of the dust? And the dust fucks up everything. I mean, dust in the universe screws up every calculation you can make. It screwed me to the wall in what I was trying to do. So anyway, the problem got very different once people began to study the cosmic background very carefully again. It's very much the same kind of story as when a deeper meaning was given to it, to the acceleration. It turns out if you don't include the acceleration in the model that makes the lumpiness of the cosmic background, and you don't include that, then you don't get the full lumpiness. The energy somehow you have to catch. I'll tell you what it is. It has to do with the acoustic oscillations of the plasma that makes the cosmic background. And that depends on the temperature and the total mass density, or the total energy density. The total energy density is what's pulling it all together again. And the mass and the temperature is what's pushing it apart effectively. So it turns out you can't make a model that has the acoustic oscillations in the right places, and that you see, the acoustic oscillations, which are the density fluctuations of the plasma, which occur at very special spatial frequencies. And you won't get the right answer for the distribution of those frequencies unless you include that dark energy as a source for more energy in the universe. And something, I don't know the number, but it's over 90% of the energy in the universe is in the dark energy.
Yeah. The dark energy is around 70%.
Is it
and
70%?
Then 25% is dark matter. and around
Okay, 70.
5%. Yeah.
Okay, I'd forgotten.
Yeah.
Okay, thank you.
Yeah.
And no, but it's the biggest piece.
Yeah.
And so you can't live without it. And I mean, the guys who discovered the thing with the supernova, it doesn't matter if they made a mistake. It doesn't matter at all anymore. It's in the cosmic background, and boy, that's God-given. You look at that tells you more than anything we've ever done with the universe. Yeah. It's just amazing. So anyway, I think those two things are big, big puzzles. And yes, quantum gravity is another puzzle, but it's not of the same character. Yes, it's important to get it right. You'll never get the event horizon of a black hole right if you don't do it. But it isn't as organic to the way we're thinking about everything in physics, unless it turns out that somehow quantum gravity has something to do with the origin of the universe, which it probably does. And that may be the other way to get it, is to get at your handle on it. I mean, let me say what that is. And that's the other future which is ahead of us in the cosmic gravitational wave business. And it's not going to be seen by the 40-kilometer system. It won't be seen by the 4-kilometer system. It's not going to be seen by LISA, which is the space system, the laser interferometer space antenna.
Yeah.
Won't be seen in that triangular system. It's not sensitive enough. It could be seen in something called Big Bang Observer. That's the thing you can look up on the web. It's an idea that was thought about by people all over in the gravity wave business. And what does it consist of? It consists of doing LISA. That means doing it in space, but with the technology of the spatial sensitivity of measuring small distances that you have on the ground. Now, let me give you what that means. LISA is able to get 10 to the minus 21 strains at very much lower frequencies than LIGO on the ground. There are other things on the ground that keep you from looking at low frequencies below, let's say, a few hertz. There's just so much other crap going on. We haven't been able to figure out how to get around all of that. And I don't think we will. It's called Newtonian gravity gradients. Just that the density fluctuations in the atmosphere, density fluctuations in the ground, cause pull forces on the mirrors, and you can't shield that. And you may be able to measure it. Anyway, I don't look up, but it isn't a tremendous. You might go underground a little bit, and that's what the Europeans hope to do in their vision of a third generation detector. We're not trying to do that because we think it's just too hard. But anyway, what is cosmic? What is the idea is the following. You could, in principle, and let me say what LISA is, the way it gets 10 to the minus 21, is it uses 5 times 10 to the 6 kilometers as the baselines, and you'll gain with the baseline. That's the strain measurement is always determined by how well you can do delta L. And if you make it delta L bigger, you can do better. That's fundamentally what it is. So it's got a very huge delta L, so they're very, very much larger delta L for the same sources. So that means that you don't have to use such a very good position sensitivity. And they can get away with a position sensitivity of 10 to the minus 12 meters. Whereas on the ground, we can't get away with a position sensitivity that's any worse than 10 to the minus 18 meters. So it's a factor of 1,000,000. So if you want to measure what I'm about to tell you, which is primordial gravitational waves, from quantum fluctuations of the earliest moments of the universe, which is a pretty wild idea alone. Crazy idea, but it's the only way people can make these waves that they know. It's made at the very, very moment when the universe was created, and before inflation really got going, or during the time inflation really got going. that quantum fluctuations in that epoch made a background of gravitational waves. The accelerations were so big. And that's the source of a cosmic background of gravitational waves, which has been carefully calculated by a lot of people now. And there are different models of inflation, but they all agree on that it's going to be something like 1 part in 10 to the 13 of closure density is the energy density in that, maybe 10 minus 14. And we're so far away from that. All those experiments are so far away from being able to do that, that you have to do something like do Big Bang Observer, which will get you to that distance, to that sensitivity. And that's a mission that I think is going to happen if, for example, these experiments with B modes, which I'll describe in a second, if they come to something that is a really good zero, it'll be hard to sell. If they come to something which is an ambiguous zero, it's not going to be so hard to sell. Now let me say what are the B mode measurements. The B mode measurements are an inference that's made about those primordial gravitational waves. And the way you get that is actually quite simple to understand. What it is if there is a background of primordial gravitational waves that came from very close to the beginning, they have expanded with the universe during the inflation. They expand along as the geometry expands. Right. There's nothing to keep them from not expanding. And when you get to the point when the 3-degree background radiation gets formed, which is sort of at the end of about 300,000 years after after the explosion, 300,000 years after the explosion, suddenly the electrons and the protons get together again. They make hydrogen atoms. The energy, the thermal energy is down to 10 eV or so. In the thermal energy, it's cool to that 10 eV, which is pretty hot, but it's gotten to that point. Electrons will stick to protons. Then all of a sudden the universe becomes quite transparent. You no longer just have Thomson scattering. You have Thomson scattering of bound electrons, which gives you a threshold that you don't get much scattering at energies below 10 to the 15 hertz. Okay, frequencies of 10 to the 15 hertz. It just the Balmer series ends it, and so what happens is that you see the polarization of the cosmic background as it is given to you by the plasma clouds that are there at that time in the universe. 300,000 years after the explosion, there are plasma clouds which are emitting the 10 Kelvin, okay? What am I talking about? The 10,000 degrees Kelvin. And now that's now 3 degrees Kelvin. They're emitting it, and they're emitting it depending on how hot the plasma is. Plasma is hot in places where the gravitational wave has caused an expansion this way. In other places, there's been a contraction. The gravitational waves make contraction, and they heat the plasma. So you get a distribution of polarizations of the electromagnetic waves due to the distortion of the plasma by the gravitational waves.
That's really cool.
And that is very cool. The numbers are terrible, okay? The numbers are, the effect itself, the anisotropy, is 10 to the minus 5 degrees Kelvin. That's the anisotropy. That's the structure that was left by the dark energy and by the dark matter. Now, the polarization can be measured in terms of a temperature also, the Stokes vector, the Stokes matrix. And it's about, you have to be able to measure about 10 to the minus 8 to 10 to the minus 9 Kelvin. And they have now gotten detectors that are good enough to do that. So it turns out that detectors exist to make that kind of a measurement from the ground or from space. The thing that's screwing it up is that there are a lot of other things that make polarization in the universe, especially the goddamn dust in our own galaxy. And it is sitting there fucking the thing to the wall, really.
So how do they do detections like that?
What?
Are they doing it with light, or are they doing it with...
No, they're doing it with the microwaves. The microwave...
Okay, through the CMB.
With the CMB itself.
Okay.
Oh, yeah.
Okay.
And the CMB, and they map the polarization. Now, because of the fact that it is a common source, it turns out the polarization patterns of the cosmic background are B modes. What does that mean? That means that they look like, when you look at a map and you superpose all these three-dimensional waves together, which is, I can't imagine the mathematics, but a computer can. And you get a map of what is the polarization pattern look like. It looks like the B modes are, which are due to the gravitational wave. One of the things that causes them is the compression of and expansion of these clouds. They look like a pinwheel, a pinwheel.
Okay.
Whereas the temperature fluctuations themselves that are there just due to thermal temperature fluctuation, they look more like a divergence, either a divergence or in or out. So they're different patterns. And you can, from the polarization pattern, map the B modes and map so you can get the ratio of what's called the B mode pattern, which is the tensor field pattern, to the scalar field pattern. Scalar field being the thermal ones, the tensor field being, hopefully, mostly the gravitational wave polarization piece. And it turns out that there was allegedly a discovery of this back 3 years ago. And it caused a tremendous stir. And what happened is people who had done this were not careful. It was, I think, a little bit of a deceit, but let it go. But the people had measured one channel. And when you do this and you want to get rid of the dust or you get rid of the synchrotron emission, there's a lot of things competing at different wavelengths, as competing with this B mode that comes from the primordial background. And you have to take care of them all. And they have different spectra. And the way you do this experiment, and people are doing it this way now, is you have to have a channel at 50 gigahertz, another channel at 90 gigahertz, another channel at 120 gigahertz. And these are channels that they have primary components from different astrophysical things that are going on between that radiation that came from 300,000 years ago, 300,000 years after the explosion, to those things that are going on in our own galaxy, which are screwing up everything. Okay? So you have to be able to do that, and the boys weren't careful enough with this. And they made a discovery, they were found out, and so now what is the best value for that ratio that's now known, that R ratio? It's, I think, about it's under 0.1, but not very much under 1. I think it's call it 0.8, 0.08, 0.08, right. And where are the predictions? God, they're anywhere. They could be 0.001. That's the trouble. So that's the most exciting experiment I think that's going on right now. These are things being done using the cosmic background at places like the South Pole, where the seeing is good, at the Atacama Desert in Chile, where the seeing is good. And I just hope those guys see something. That would be absolutely spectacular. It'd be the most interesting of all the discoveries. Yeah.
So I definitely want to ask you more about the cosmic microwave background.
So,
I mean, a lot of this is coming out of general relativity, and you're talking a lot about pieces of dark matter. But how do you feel about gravitational or modified theories of gravity to explain dark matter? I know they haven't gotten a lot. You don't like it?
Well,
okay.
It's too easy.
It's too easy. Okay.
Yeah. I mean, look, so you can invent what you like. But then you damn well better have a way of seeing something besides the effect that you're trying to explain.
Right.
And that's one of the big problems with all that stuff. They explain one thing, but they can't explain anything else. And there's the motivation isn't good. But anyway, the reason why I feel that way is that this is just a hunch. Everything people have done with Einstein has proved him to be right. I don't know how he did it, how it happened that way, but everything that he says, even when he made the mistake, and he says he did make a mistake, but then the mistake was corrected, has come out, general relativity has come out on the money. And the fact that in high energy collisions now, it's on the money. God damn it, how did it do that? How did Einstein know? It's just... So don't give me any other theories for a while.
That's fair. For the cosmic microwave background then, I know that you did a big experiment with the cosmic microwave background.
I worked a lot on it,
Yeah. How does it feel going between that and going to something like LIGO? I mean, these are two hugely important experiments.
Look, that is a complicated story about the dynamics of me being at MIT as a young professor. And that had to do, I probably would have not gone into studies of the cosmic background hadn't it been for tremendous amount of urging by people who were older than me that I had to do something and write a paper about it. And they said, you're never going to write a paper that has a result about gravitational waves. Just forget about it. You got to have a paper, otherwise we're going to have to fire you. And I was told that over and over again by a guy named Bernard Burke, who was a love-hate thing between him and me. But in the end, I think I owe him a lot for at least telling me the truth. And so I taught general relativity for the first time in 25 years at MIT in '66. And in that course was a couple of people who we all fell in love with cosmology. I mean, it is just a wonderful topic. And you pick up any book on general relativity, go to the cosmology chapter, and all of a sudden it becomes living, wonderful science. Before that, it's mathematics and GUI tensor relationships, which is bad stuff. But you have to learn it. But then it just blossoms into this incredible field. Right. And we all fell in love with it. I mean, I fell in love with it. And the kids, obviously kids, were my age almost. But they were gentle, very sweet souls. They let me bumble along because I didn't know any mathematics. And that course also is what invented LIGO, but leave that go. So anyway, no, we fell in love. And there were two guys in that, well, one guy, Dirk Milner, who was absolutely, we fell in love with the cosmic background. And it didn't take much. If we had to write a paper, I talked to Dirk, and I said, let's try to find out if it really is thermal. We thought that would be much easier than measuring gravitational waves, which it was. But it still was a hell of a hard experiment. But at the time when we were getting interested in it, the only thing that was known was the Rayleigh-Jeans part of that curve, the part at low frequencies. And it was absolutely crucial to find out if it turned over like a black body. And we had people here like Phil Morrison, who was dead against it. He was a steady state cosmologist. He says it's all bullshit. He didn't just use those words. He was more genteel. He said it's crap, okay? That there is no Big Bang. That's complete nonsense. And he said all that stuff this is not proof of a Big Bang. It's proof that there's a lot of dust around the Earth. That's all it proves. So, I mean, I went to him. He says, it's hardly worth doing that experiment. You'll find dust. So I said, yeah, well, we'll go find out. And it took us, I hate to tell you, 5 years to find out with balloons. And then we did Kobe, and that was the thing that really nailed it. Yeah. That took 20 years more.
Yeah. Well, I think that's a really amazing story.
Yeah.
And,
yeah. Look, but what happened is during that time I was able to have enough students that I could start a student on the gravity wave experiment, and when he or she got to the point where, like, God damn it, I need a degree, okay, I could switch them to the cosmic background experiments, and they could get a degree out of that. Because it wasn't just building apparatus. They were flying balloons, getting new data all the time. And Kobe. But Kobe was so long, very hard to put students on it until the very end. So I played a game, and the first time I ever put students on the gravity wave thing was in 1986. That experiment started in 1972. Finally, I had the courage, and it didn't turn out well. Because the kids, they were two guys, measured gravitational wave. They set upper limits on gravitational waves using a little tiny prototype we built. And they got hell from the PhD committees. And we found that Francis Lowe, who is now unfortunately dead, and was another one of these theorists who was very, very smart, but unkind in a way. He asked the poor guy who had slaved on this experiment for 5 years. He says, what's the impact of the experiment you did? And the poor guy said, well, no. And he said, well, the sun didn't blow up. And Francis looked at me, and he says, how could you give people a problem like that? Okay?
That's rough. A little close to home.